Hi, I'm Alex from the Human-Computer Integration Lab, and today I'm super excited to share with you a new haptic device for altering the friction of real surfaces. Here we can see our user wearing a mixed reality headset, and he's playing this driving game by sliding his finger on the table. Now, when he drives through this virtual puddle, his car spins out, and the table suddenly feels slippery. But wait a moment. How can this ordinary table feel slippery? Let's drive through the puddle again, and I'll reveal our secret. We've been depositing a liquid coating onto the finger pad. This coating lubricates the finger, resulting in decreased surface friction. We call our approach Stick&Slip, and this is something that we, myself, Jacob, and Pedro, have been exploring here at the University of Chicago. Our work is motivated by friction's importance to our tactile understanding of the world, and that liquids offer a great solution to altering friction. As an example, when I grab this glass, my finger pads immediately feel its surface friction, and I know exactly how strongly I need to grasp it in order to pick it up without it slipping. Now, if the glass were wet, I know that I need to grip it harder, because its friction is reduced and the glass is more slippery. So given friction's importance, it's no wonder that haptics researchers have been interested in friction as a way of providing feedback to users. There have been two primary ways that researchers have controlled surface friction. The first is ultrasonic vibration, where vibrating a surface very fast causes the finger to contact the surface for less time, thereby reducing the friction. The other is electrostatic adhesion, where charging the surface with a voltage attracts the finger to the surface, thereby increasing the friction. There have been numerous research devices, like these, just to show a few, and even commercial products based on these approaches. However, neither of these look like the example of grabbing a glass or any other everyday object. They're usually just added to special purpose devices, like tablets. So, let's consider this challenge. We want to alter the friction of everyday objects so that anything we touch can have friction feedback. We could start by simply adding these types of actuators into the objects themselves. But this is impractical. We cannot cover every single surface with haptic actuators. They're expensive and they're power hungry, and they would need to be customized for every object's geometry. The list goes on. Moreover, to both increase and decrease the friction, you'd need to combine both of these actuators into a single device. So while these traditional approaches are perfect for tablets, they don't work very well for everyday objects. To overcome these limitations, we looked beyond the scope of these traditional actuators toward liquid coatings. In our approach, we deposit small droplets of liquid onto the side of the finger. These coat the finger pad and create an interfacial layer between the finger and the surface. Depending on the liquid that we choose, we can either make it feel more slippery or more sticky. And after some time, this liquid dries up and the friction returns to normal. So our device can do both increasing and decreasing friction within surface's material. Therefore, the liquid coating influences the friction regardless of the surface that the user touches. And so, unlike these prior approaches that require adding actuators to every surface, our liquid-based approach can change the friction of practically any non-absorbent surface touched by the user. And so this is precisely why we explore this liquid-based approach. Now, for all of this to work, we really need to choose our liquids very carefully. To guide our selection, we set goals of optimizing for two parameters. First, we wanted liquids that can increase or decrease friction across a wide range, a sort of friction intensity. And secondly, we wanted liquids that are practical to use. That is to say, they simply evaporate away or they can be easily cleaned. As an example, something like oil might make for a fantastic liquid for decreasing friction, but its practicality is very poor because it doesn't evaporate. So it might not quite meet our goals. Additionally, we had some key qualifying criteria for selecting candidate fluids, such as skin safety, cleanliness, low viscosity for pumping, and more, as detailed in our paper. So from these criteria, we curated a list of 9 candidate fluids to evaluate. Firstly, we include water as our baseline liquid. Additionally, we include oil as an example of a great lubricant in order to help frame our analysis. We also found water-based liquids, such as lubricants, which we expected to decrease the friction, and thickened water, a viscous gel which we expected to increase the friction. We were also interested in isopropyl alcohol, or IPA, and acetone. While people don't commonly think of these as lubricants, we suspected that their rapid evaporation could be even be found in cosmetic products. Finally, we tested sugar water and honey mixed into solvents like IPA. Most of us have felt the stickiness of sugary liquids like fruit juice. This is caused by sugar's hydrogen bonds with water. We wanted to see if we could create thin, adhesive layers on the Fingerpad by mixing sugar water with IPA. So now that we've got this long list of candidates, how can we narrow this down to usable, sticky, and slippery liquids? Well, we ran a tournament. We designed 4 experiments to evaluate each liquid's ability to alter friction as well as their practicality. So let's start by looking at the influence each of these had on friction. To evaluate the effect of each liquid on friction, we built a sliding mass tribometer to emulate the friction of a finger during a light, exploratory touch. It consists of a sliding mass with an elastomer skin to emulate that of a finger, connected to a hanging mass via a fishing line and a pulley. By adding weight to this hanging mass, we can see how much force it takes to overcome the friction between the sliding mass and the surface. We can then estimate coefficients of friction by measuring the hanging mass required to cause sliding, as well as the acceleration of that sliding mass. And the acrylic, we can study the effects of the different liquids on friction. So here's the plot of results for static friction. The x-axis shows the change in static friction compared to the no-liquid baseline. Bars that go to the left indicate a reduction in friction, while bars that go to the right indicate an increase. Looking at our baseline of water, we can see a slight reduction in static friction. The greatest decrease in friction came from oil, followed by IPA, acetone, and water-based lubricant. The greatest increase in friction came from sugar water, followed by the honeys in IPA and thickened water. We see a similar trend for the kinetic friction. Excitingly, we find that we can modulate friction by more than 50% in either direction using liquids. Another exciting and perhaps unexpected result is that the acetone and the IPA were nearly as lubricating as the oil. So now we want to cross-examine these friction performance results with a measure of practicality. Let's look at evaporation. To measure the evaporation, we pipetted a droplet onto a weigh tray and measured the mass over time. Here are the results, where the x-axis shows the percent of liquid that remains at a given time, either after 5 minutes or an hour. Looking first at our baseline reference of water, we can see that even after an hour, most of the water is still there. And this trend is generally observed for all of the water-based liquids. In contrast, nearly all IPA and acetone have evaporated away in just 5 minutes. In the case of the honey that's been mixed into IPA, we observed that the IPA evaporates out of the mixture, leaving just the sugar residue behind, which corresponds to its weight concentration. At this point, we can easily eliminate unsuitable fluids like oil and water-based liquids because they just don't evaporate as quickly as we'd like. This leaves us with liquids that both generate slippery and sticky changes in friction, but are also practical to use. For slippery, we have acetone and IPA, and for sticky, we have the honeys mixed with IPA. Please see our paper for further characterization. For example, we show that these sticky liquids can be washed away easily with a similarly sized droplet of water. Now, to leverage these friction effects in an interactive device, we built a wearable droplet generator. The user wears our custom PCB, battery, and antenna on their wrist. Additionally, they wear 1 milliliter vials of our slippery and sticky liquids. Micropumps pump this liquid from the vials to the Fingerpad, where our user wears our microfluidic device that has nozzles that generate the droplets onto the Fingerpad. Importantly, this droplet generator only contacts the sides of the fingers. It leaves the user's Fingerpad free to still feel the world. Now, to see more of what this device enables, let's return to our user in mixed reality. Again, the user feels slippery going through the virtual puddle, which we now know is from alcohol. Now the user goes through a different virtual effect, honey, and feels the friction increase. In this case, we're depositing our sticky liquid, IPA mixed with honey, in order to render this honey's increased friction on the table. Since our approach lets users still feel the real world, they can easily feel the texture of those toy speed bumps, and we can also easily augment the friction of this toy ramp to feel slippery, like ice, without any modification to the toy itself. This would be impractical to do with electrostatics or ultrasonics, due to requiring custom actuators on every surface. With our approach, every non-absorbent surface can have its friction altered by our wearable. And so, while I use mixed reality props here as an example, we can alter the friction of everyday objects. So we actually brought in participants to try out this exact mixed reality scenario. They're playing this game while wearing our device. For both a no haptics baseline and the stick-and-slip condition, participants rated their sense of immersion, enjoyment, and sensory engagement. Here are the results. We found that stick-and-slip provided a more immersive, enjoyable, and engaging experience than the baseline. These ratings are further supported by comments from the participants. For example, in support of improved immersion, one participant remarked that seeing the visuals line up with the feeling led to better immersion, and another said, "If I were driving through ice, it's how I'd expect it to be." Similarly, for enjoyment and sensory engagement, another participant mentioned that stick-and-slip sparked more childish excitement. While a potential novelty effect might be expected, all participants ended up preferring stick-and-slip, which gives some indication that participants felt that the fluids were not unpleasant and did in fact add to their experience. These initial results are very promising, and feedback from participants informs some more important future work to address, such as improving the onset speed of the stickiness and removing residue, though only 2 participants commented on this. So we found a few domains where this approach is useful. In addition to mixed reality, we've also been exploring tool use and prop-based virtual reality. For example, this user uses it to assist him opening a step container. At first, he's struggling to open it, so he now uses his watch to deposit sticky liquid on demand. As the friction increases, his grip improves, and now he's able to open the container. This is also compatible with prop-based VR, where we can render haptics of a broken water pipe directly onto a physical prop, like this PVC pipe. So here, he can feel the slipperiness of the water, but when he goes to seal up the pipe with some putty, he can now feel the stickiness of that sealant on the pipe. Today I've shown how we can get friction feedback out of these special purpose devices and onto everyday objects. This opens up applications in mixed reality, prop-based VR, and even using tools. We achieve this by thinking outside the box of traditional actuators. Now, unfortunately, it isn't just friction-based haptics that's been constrained to special purpose devices, but also more typical things like vibration, heat, and more. My PhD research has focused on this question. How can we make haptics scale to be ubiquitous? That is, how can we give haptic feedback to every object in our environment? Well, we've seen sensing weaved into our daily lives. We can't yet say the same for haptics. And I argue that this is because we've largely been limited by these stock actuators, like vibromotors and Peltiers, and that we need new kinds of haptic actuators designed specifically with scale in mind. For example, in Magnet.io, I re-engineered vibration actuators into passive patches that can be distributed throughout environments and without batteries. In Thermal Grasp, I developed thermal feedback devices that can overlay temperature sensations onto real surfaces. Now, to conclude, I want to emphasize that these approaches may be unconventional, but maybe that's exactly what we need to push haptics into ubiquity. I'd like to thank you all for your attention, and thank you to my amazing collaborators, Jacob and Pedro, for really enabling this work.